Hi everyone, my name is Alexander Ioffe. I'm here to talk to you about Quoted-DSLs. And this is sort of part one of what I thought was eventually a two-part talk. Maybe I'll do that at some point. I like to say there are two parts of Quoted-DSLs. There's the part where you put the rabbit into the hat and the part where you pull the rabbit out. In this one, we're learning how to put the rabbit into the hat. But anyway, I am the maintainer of a library called Quill. It's a database language integrated query library, and a lot of the concepts I'm about to go through today are used in Quill, but they're much, much more general purpose. So let's get started. A couple of things, actually. First of all, most of the examples I'm going to be giving are from Scala 3, Scala 2, because I'm going to be going into macros very, very heavily, and actually touching on some of what Vincent said earlier today. And also, I am glossing over many implementation details because, as you've seen, these trees can get quite deep and can get quite nasty, so I'm doing lots of simplifications. I will post these slides with the actual real code samples, and then you can sort of correspond, but I do have to make lots of simplifications for this stuff to be sane on slides. But before we do that, why should you care about any of this? Why should you care about quoted domain-specific languages? Why should you care about domain-specific languages at all in that case? So the answer is quite simple, right? If you've got some kind of business domain, let's look at some trivial business domain. This is right, strike prices and underlying prices of equities. These are, imagine the world only consists of calls, no puts in the world. But we just want to calculate, some weird label, which is the difference between the strike price and the underlying price / the name, whatever. Imagine this is some financial industry mnemonic of some kind. Okay, we want to calculate it. So the thing is that a business domain, it turns into a domain-specific language the second that it has some kind of reasonable complexity about it. All right, so any kind of business model turns into a domain-specific language given enough complexity. And this happens very often. So here's an example of what a query would look like, right? So you were trying to, just subtract the two parts from one another and then concatenate on some stuff. Right? But imagine we want to do this with 20 billion different records. Right? That could get quite big. So we need to take this kind of logic and ship it off to some compute nodes somewhere, to some cluster somewhere. And what's the typical model of doing that? Well, this is the typical model of doing that, right? Where we need to package it up into a jar file of some kind and copy it over using some kind of utility, and then eventually we run it. And right, that's just so that this little execute thing can run on some compute nodes, right? We need to do all this sort of ceremony here. So that's the Spark model, but it's almost like the EJB 2.0 model, where you had some kind of enterprise container that you would need to copy your jar down into. Which is why a lot of people that are into data science have said, no, come on. We need to be able to run ad hoc queries and introduce this thing back into for example, the big data space. And then, of course, it seems to be nice, but this turns into this very, very quickly. So what we need to do is we need to think about, wait a minute, this needs structure. We cannot do this in a way that this thing is a giant string. So I've devoted a lot of my career to Quill and taking this thing and deconstructing it into ways of representing it in a sane, structured way that is structured in your host language, i.e. Scala. The key to that is being able to have a structure that exists within Scala that is native to the Scala language, or native to whatever language you're trying to do it in. But at some point, you need to convert it down to SQL or some serialized form that you can, ship off somewhere, that you can introspect, do something about. So eventually you need to build some kind of data structure that can represent that. So here's an example of what we would call an intermediate representation in Morpher language, or an abstract syntax tree. And so the idea is, right, we sort of represent the fact that we're doing this minusing thing here, and that we're, whoopsie, and then we're calling these two keys here, and then eventually we're concatenating it onto some strings here, right? The syntax tree represents in some way the operations that we're doing, so then we can take something, we can take the syntax tree and do something with it. So, okay, so here's our syntax tree down here, right? We use this grammar, because that's what a syntax tree is at the end of the day. It's a set of grammar semantics. And then we have to convert our code or our query that would look like this into something that looks like this. Well, the question is, what do we want to do with that? Well, we turn it into SQL, or again, we can serialize something like this intermediate representation, and then we can copy it to some nodes, and we can run it, and it stays structured the entire time. And that's the whole point, is that we don't need to remove this structure. We have it forever, essentially, until eventually we decide to lose it, like with the SQL case. So, okay, eventually we'll copy it over to some node somewhere. We'll build some kind of evaluator. This is a sort of a trivial example evaluator of what does this. So we just take this thing and recursively evaluate it. Of course, real evaluators are going to be 1,000 times more complex. But here's the question, right? And this is where we go into embedded DSLs, EDSLs, reified optics, that whole class of things. The issue is that, well, how do we actually pull it off? How do we actually go from here down to here? How do we do that? That's the problem, right? What is it that we have? What is it that we have up here? Okay, let's start with this part, right? This is subtraction. We're subtracting two things from each other that are integers. Okay, subtract two integers. How do you introspect that, right? How do you introspect a statement that is just something minus this thing if these are just simple data types like that, right? You can run that operation, you can do that subtraction, but there's really not much that you can know if you're just looking at some unevaluated subtraction of two integers. You can't know what those two fields are. So what you need to do is you need to build some kind of something that provides a way to introspect it. So you need to build some kind of container. Now, there are certainly way better ways to do it than I'm doing here. Just, I've designed this kind of EDSL just for the example of being able to have identical code between the QDSL and the EDSL, just so that we can sort of make an apples-to-apples comparison. But the idea here is that we want some kind of thing, some kind of container that will be on some kind of data type, and that container will essentially provide us the ability to describe our operations. Also, at this point, we probably want our syntax tree itself to be typed. Okay, right, how do we actually write this thing? It's not necessarily this bad, right? We can make all sorts of ways to make creating this thing easier. But what does this give us ultimately? It gives us the ability to, well, convert from this to this, right? Because this minus operator here is on the value class. It's no longer on straight up integers. So here's the way the minus operator is implemented, right? It's some extension, or you can define it on value itself, but it's an operation that basically says, don't do this, describe it. So we're describing it. We're describing subtraction. And this says, produce a node for us that is the description of this computation, okay? So then once we do that, we then are able to take that and splice it, and then we continue this concept, and we do it for everything else. So the toString is also part of our grammar. We say the method toString returns a description of that, and the concatenation methods return descriptions of that, and then we have further and further and further more descriptions of that. So here are all the operators we built, and the operators basically return descriptions of the operations. So now we can actually build up this abstract syntax tree, but at the cost of a little bit of complexity, because we are no longer dealing with simple integers and strings. We're dealing with containers and potentially different kinds of containers that have these things. So then immediately our types are no longer simple. But okay, fine, IDEs can help us. IDEs can help us with the types of these things. So it's not, there are advantages and disadvantages. But this is the direction that we want to go. But now, to go further, we run into certain complications. Like, what if we have this AST of string thing and we wanted to implement some kind of method on it that takes a lambda? Right? Like, what if we want to implement map? Right? How do we do a map of AST of string? And, okay, well, that depends on what our expectations are. We could have very low expectations, or we could have slightly higher expectations, right? If we have high expectations, like being able to see this lambda here, then we might be in trouble, because again, remember how we can't see what two integers subtracted from each other are before that actually happens. The same thing, we can't see inside of lambdas. We can call them, but that's basically all we can do with them. We cannot see inside of them, which is why, of course, we need to build all sorts of different kinds of mechanisms for being able to serialize them and introspect them, and this has some extremely fundamental implications on how Spark is designed, because we cannot see inside of closures necessarily. So if we want our domain-specific language, or the grammar of our domain-specific language, to be able to encode these kinds of things like a map function, right, this thing needs to be right in there. Right? What can we do with this closure? Well, we could stick it right into our grammar. We could do that, but there's not much else we can do. Right? So there we go. We've added this map thing into our grammar, and we have this method here that is the evaluation of that. That's basically all that we can do, at least with this particular encoding of the grammar. And that's basically it. Now, there are other ways of doing it. There are completely different ways of looking at all of this from the ground up, where you can start encoding logic inside of container types and make all sorts of interesting lambda functions that you can't actually call, because it's container types, and container types don't actually need that thing to call it. With flatMap, and the second you go monadic, that becomes more difficult. But there are still ways around that. And well, at some point, what you need to do is you need to start using more type classes and start putting more logic into type classes than the method itself. And this is actually a lot more like Slick. This looks a lot more like Slick, because you have these query container thingies that do the real thing of the actual operation. Now, is there a different way? Now, there are plenty of good ways to do embedded DSLs, but the question is there another way? Can you go back to that way of doing simple Scala types? Can you do that? And there is, but you have to use macros. And because macros look at unevaluated code. They look at trees of code. Right? What is code ultimately? Code is some ASCII characters that we enter into some kind of text editor or IDE. What do those things become? Once they're parsed, they become trees. So the compilers see code as trees. Right? So we have some kind of expression. That expression turns into a tree. That goes into some kind of quotation macro that can then transform that tree of our unevaluated code into something that is like this grammar that we saw before, right? So here, right, eventually we produce that, and eventually we can take that and, spit it out somewhere outside of our macro and put it into some evaluator. Now, the vast majority of what I'm going to be talking about for the rest of this talk is the former part. Is how the heck do you actually look at a Scala expression and then parse this thing into something that can represent this structure, this grammar. So the same process that we just went to with embedded DSLs, we're going to look at that with quoted DSLs. And we're going to look at, again, how the parser, or how in fact, the Scala compiler, which has a parser in it, how the Scala compiler looks at code. How does the Scala compiler see our code? What is our code to it, right? So imagine that we have this kind of macro or an entry point called this query thing. So this query thing is where some expression of our code, right, this is our expression that we've been working with from the beginning, this thing takes an expression. It looks at an expression of code and it says, okay, I see an expression. I can do something with it. And then we're going to take that, and into that we're going to build in the logic to take this expression and tease it apart and eventually yield the kind of grammar that we want. Okay, how does a compiler look at code, right? Something dot something, right? Person dot name, right? What is something dot something, right? Well, in this case, the thing before the dot is an identifier. A variable is an identifier, a method. It's an identifier of some kind. It is an identifier. That identifier actually has a type inside of itself, but not relevant yet. And then we can select a property from that identifier. So every single time in life that you have ever done something dot something, you have selected a property out of an identifier. Right? Every single time you've ever done that, this is what you actually have done. Okay? Now, we can do something else once we select something from something, which is we can actually apply arguments to it, hence a function, right? So we can apply stuff to it. So again, every single time you've called something dot something and passed something into that, this is what you've done. You essentially said select this term from this identifier and apply certain arguments to that, right? Okay. Now, by the way, it could be multiple arguments. That's why it's a list right here. Okay. Now, let's look at some other things, right? Simple things like constants, right? The string foo is a constant. Okay, what is a constant represented as inside of the compiler? It has a data type for constant. Right, it's actually literal of constant. Again, I'm glossing over some details, but there's this constant type. Okay, now, how do we deal with this? Okay, remember query? Here's our entry point. Here's something dot something. How do macros work? Right, we have this entry point. We select a property from a field, and now, what can we do? What can we do inside of a macro? Well, we can match on it, right? We can say, okay, what comes inside of this macro, right? Here's the macro. Here's the implementation. We've seen this from Damien's talk. There should be a using quotes thingy here, okay? But what we can do then is, well, we know we are expecting a something dot something to go into this macro. We know that the something dot something looks like this, and so we then say, okay, this is the pattern that we're expecting. Match on this pattern. I know this pattern. I know the pattern of data dot underlying price because I know that's my business domain. And then I know what to do with that. I have this thing called key in my grammar that then yields underlying price. So I know what to do with this pattern, match on it, and return the construct within my grammar of it. Okay, but we kind of want something more generalized than data.underlying price, right? That's kind of one field. We don't want to have to enumerate all the fields, so we can generalize. So we start generalizing. Now, we don't want to generalize too much, right? Because we want data to be of a type that we recognize. So let's say, for example, we know that remote data is going to be the class type, so we can check on the class type. So we say, if it is a class of this kind, and we're selecting a field from this kind, then we know this is a type of thing in our grammar called a key, or selection of a column in that particular row. Okay. The other thing, just as a formality, we did as term here, making it as an extractor will make life much better for us in a few slides. So I'm adding it right here. You have to basically take the as term and write it as an extractor. Please see slide notes for how to do that later on if you'd like. Now, let's make some more space. And also, to make our life easier in a few slides, we're trying to write a recursive parser, right? The same way that we needed to evaluate this thing recursively, we need to parse it recursively as well, because there are going to be things inside of things inside of things. Okay. So, and also we want to catch all in case we can't match on something. Quick thing. What comes out as an abstract syntax tree? We need to return an expression of an abstract syntax tree, because wait a minute, macros don't actually return values. Macros return code, right? Code goes in, code goes out. We can't return values. That's sort of a problem. I've kind of been lying about that to you until this moment. But we will figure this problem out very, very soon. However, first, let's look at parsing some things. We'll just do question mark, question mark, question mark as a placeholder for now, because that's totally fine. Anyway, so let's look at subtraction, right? Subtraction of two simple Scala integers, right? Remember that Scala does not have operators. All operators are just functions. So when you do minus, you're doing dot of that, and you're applying of that. So basically it's select the minus operator from the left-hand side and apply the thing which is the right-hand side as the argument. It's just a function, right? And we just match on that. So now we've matched subtraction. And then we recursively go into the left and the right, which are going to be identifiers or property selectors, right? That's why we have our recursive evaluator. So, okay, let's keep going. Right? Oh, by the way, these are term things. This is an expression thing. Remember earlier we were dealing with terms versus expressions, so that's yet another thing to keep track of, but that's fine. We just have simple converters. The other fun thing is that we can use higher level APIs. This is the quotation API, and Damien's slides also mention this, right? We can actually match inside of quotations. So we don't necessarily have to do selective apply of selective apply of selective apply from everywhere. We can match on higher level things. So this is an example where we can do it like this instead. And in fact, we're going to keep doing it like this instead, right, to match invocations of the toString method, and as well as the concatenation of the left and the right, right? We're starting to build up a nice recursive parser here. Okay, and then, string constants, right? How do you match on constants? So remember, literal of string constant. And the reason why that is because the language has to track the type of the constant, because in JVM they're primitives. Long story. But anyway, so okay, we match it like this. We can also do it like this, slightly less efficient. So once we have that, guess what? A constant is just a string that the compiler knows about ahead of time. Right? It's the compiler knows what this thing is. It's not just some identifier that's holding the value of some variable or method call, right? The compiler actually knows what this thing is, which is why that's why we're bothering like with all this literal string constant stuff, because once we do that, we can actually get the value of the string, right? We represent that as a constant in our grammar. So our grammar understands constants. Okay, right? Because like constants is something that you will want to have in any kind of domain-specific language, in any kind of grammar of a domain-specific language. Okay, now also everything we've done on the left-hand side, these quoted things, these term literal things, right? Everything on the left-hand side, that's all Scala stuff. Everything on the right-hand side, that's our grammar. So we can see what's what. Okay, now let's look at our entry point again. Remember, we no longer need to have containers of things. These are now simple types. These are simple Scala types. And because this query thing is a macro, because it's a macro, it can look into the expression. And we don't necessarily need to create these container types and these EDSLs that are then able to sort of go backward by producing descriptions of computations. We have the entire description of the computation in here, right? A macro knows the description of the computation that is going into it, because the description of the computation is just the expression tree, right? That's what makes macros so useful. So these can remain simple Scala types. It's just integers and strings and operations of them. And we can take this thing consisting of simple Scala types and then build up the expression of that down here in our grammar, right? We don't need more complexity than that. We just have to bear the complexity of writing this sort of recursive parser. Now, what about going into like a map function, right? That was when we had a lot of problems before. Can we do this, right? Well, let's define what we want for a second. Remember, these are simple Scala types, so a map on a string is going to give us a list of characters. That's not really what we want here. So we want some container type. We want some container type on which we can describe map. In Quill, this would be the equivalent of like query or something like that, right? We want something sensical that we can capture a map from. So let's just define this. Note, this doesn't need an implementation because we're not going to be evaluating it. This is what's so wacky about Quoted-DSLs. We don't need implementations, right? We're not ever going to evaluate this thing. And so what we can actually do is we can actually throw a big exception at the end of it if somebody uses it outside of our macro, saying, no. This is never supposed to be evaluated. This is only ever supposed to be used inside of this query macro that will then parse it and extract some meaning from it. This will never actually be called. So we would call it maybe a phantom container or a phantom type. I don't like the term phantom type because it sounds mystical and esoteric when it's not. It's just something that we don't ever evaluate. But anyway, so we kind of, let's do this, right? Let's go into this kind of construction. So we say that we have this map thing on this entity container type. Now, how do we actually match on this thing inside of a macro? So, okay, we already know what's at the top, right? Because we've already seen apply and select and sort of all of this stuff down here that represents this thing at the top here. It's all kind of trivial already. Sorry. So we have an understanding of what's going on up here. What about in here? Right? What about, well, down here, but let's look at in here. What is this value thing? It's an identifier of some kind. How do we represent that? How do we represent that in our grammar? Okay, we're not sure yet, but let's just say it's something. But the rest of the expression we know, right? The rest of the expression is just select of plus and apply it to this thing inside of here, which is a constant. So let's look at inside the lambda. Let's look at that whole thing. Well, we know the first part. We know the map part, right? Because the dot map is just a selective dot map from the previous thing, which is that entire left-hand side, and we're applying some arguments to it. Okay, so what's inside of that? Well, it's just this lambda 1 thing, right? This is what the compiler actually sees when you give it code with a lambda. This is the construct that the compiler sees. There's obviously, there's a lot more detail here. There's a lot more detail inside of lambda 1. But just fundamentally, you think about it, in the compiler syntax tree, this is what the compiler sees. Lambda is just a node, it's just another node in the compiler's tree. And it sees that node, and the body of the lambda is just another node inside of that element. Right? Lambda 1 is a node, and we see the body of the lambda, right here, the value plus this constant slash inside of there, and we just see that as the compiler inside the body of the lambda, because that's how ultimately the code is represented in the compiler when it's parsed. So we can just take this thing And we can further write a parser to parse this lambda thing, right? So what do we need? Remember, we have this map node thing that we've decided to introduce to our grammar. We want to understand what's going on, so we set some variable, and then we get some variable inside of the value, right? Inside of the body of the lambda. And in our grammar, that's enough to understand what lambdas are. It's just this thing where we then say, we have made a new variable that we can then use inside. Now, here's the funny part. The assumption here, of course, is that this variable is immutable, which we can make in this case because we have sort of built in that assumption into our original domain-specific language. So we can make this assumption perfectly. So then if we just make that assumption, we add these elements to our grammar right here. So then all that we have to do now is to parse this expression. So let's do that, right? Let's parse this expression, and then finally, when we see this expression, this is what comes out, right? So this is what the Scala compiler sees. This is what we need to return, right? This has some kind of variable in it called value. We set this thing, and then we can use it inside of the body, right? Whenever we see identifiers inside the body of the lambda that are using the variables that were declared in the lambda, we know that it's a get variable inside of our grammar. Well, here's how it works. We just add yet another clause into our parser for this. So we have another as term thing, and we do the apply of the map from that. There's some additional things in here, but basically it's apply of map, and then the lambda 1 is the list of arguments that's going into the selector of .map, and then inside of that is the lambda 1, and inside of that is a lambda body. So we know where the lambda body is, and we just recurse into that. Right? Here's the lambda, here's the body, recurse into the lambda body. And that's it. It's a completely transparent container, and we know what to do with it. So we just yield this node map. We've recursed into the lambda body, and then of course there's all the stuff before the lambda before the map function that we need to get into, right? Over here on the left-hand side, and then of course there's the actual variable that's used for the .map function. So then, right, we build this kind of recursive parser, and then guess what? We just use it. So when this entity of all of this stuff in here, .map, concatenate the slash onto it, et cetera, right, we just pass it into our query entry point into the macro, goes into the parser, parses it recursively, and voila. Here is our grammar coming out. So if you've ever used Quill and you've seen quote, this is how quote works. This is what quote does on the inside. It has a recursive parser that sees what you've passed inside and can then return an expression of some kind of grammar. And there's all the places where we're using that some kind of grammar. Okay. Remember this thing that we saw where we needed to return expression of an abstract syntax tree, but this thing was an abstract syntax tree, and I didn't quite show you that detail. Let's go into that now. Okay, how do we do that? Well, here's what we start with. We start with this abstract syntax tree. We need to yield an expression of it. Okay, well, abstract syntax tree is just a bunch of stuff that it could be, right? It's a coproduct. So we just go through every single thing that this could be, and then turn that into this, right? Experify every single thing that it could be. And the high-level API for Scala 3 helps us a lot, right? We just say the same thing inside of this quote thing, and then recursively do that, right? We just say subtract is quote of subtract, and this recursively quotifies everything, right? So this is just a very simple way of going from this AST to expression of AST. There are more professional ways of doing it. There's this toExpr thing that they've implemented as part of the Scala 3 API, where you can do this with type classes if that's your ball game. But anyway, so let's just snap it in, toExpr at the end, and we just convert it to expr of AST. And that's what allows us to take this runtime value of AST that is running in our macro, and then return it as a compile time value, expr of AST, back into the call that the user has made. So it's our macro runtime actually needs to unmacroify whatever is coming out. And this is how it's done it. Also, one other note, because the logic that we're returning is only this grammar, we can kind of return any type we want. So, for example, we've constructed this query container thing that is supposed to hold that. So we can just use this quote syntax. Okay, if we want a container type to hold our syntax tree, we can actually attach types to this thing. And again, this is how Quill does query. This is how Quill does query of T. Query of T doesn't have anything. It doesn't do anything. There is no meaning of the parameter of a Quill query. The logic is inside the abstract syntax tree. So whatever kind of type makes sense for your application, that's what you return. It doesn't matter. That's not where the real evaluated logic is. Okay. That was a whirlwind tour. So, quick recap, right? We can have an expression with simple Scala types. We can create entity containers as we want. And if we have this construct, which is this macro, that can introspect this expression, it can see everything inside, and it can yield a grammar of our choosing by recursively parsing what the Scala compiler sees is the representation of this code, which is the Scala compiler's abstract syntax tree. We then take the Scala compiler's abstract syntax tree and we convert it into our syntax tree, or our ADT, the thing that makes sense in our domain. What is this useful for, right? Why do we practically want to do this? Well, here's why. Simple types. Again, we can build a domain, a business domain, that actually has simple integers and strings and doesn't need complex types, and we can take that business domain and express business logic in it. We can catch things. We can catch things that are completely impossible to catch. If we want to say you are not allowed to typecast, by default, you will not be able to typecast. Right? If you try and typecast, this will explode, right? But you can go further, right? Same thing with system.exit, right? You can't really catch system.exit in an embedded DSL, right? Because it's there, right? It has to be evaluated, right? You can even make helpful error messages for users like, don't do this, and actually guide the user in writing your product and tell the user, no, you shouldn't be doing this. Here's what you do instead, for example. And then finally, you can actually view the grammar at compile time. So, oh, I translated it, I have the grammar. You can actually, the second the user presses the compile button, you can show it to them. You can show the grammar that they've done. Anyway, and by the way, Quill shows not the grammar, but the query, which is like a few stages forward of it. So you can do any kind of other product you want from the grammar. So there it is. advantages of quoted DSLs. And I would like to give again, a great heartful thank you to John, to Adam, to Sandra. Thank you so much for supporting me. Thank you so much, Damien. Thank you so much for supporting me. Thank you, Zyverge. Thank you to the Capital One folks. And thank you to all of you in the ZO community. Have a wonderful evening.